Hello, and welcome to our lesson introducing conditional probability. Today we are going to deepen our understanding of probability by exploring how conditional probability works and how to apply it by restricting our sample space to specific parts of a diagram. In this lesson, we'll build on concepts you are already familiar with and introduce powerful techniques to better handle complex probabilistic scenarios. We'll start by understanding the concept of conditional probability and explaining how it differs from general probability. Then we'll illustrate how restricting our sample space to certain parts of a diagram helps us calculate conditional probabilities. After that, we'll go through some practical examples and apply this new knowledge to solve problems. So far, you have built a solid foundation in understanding probability by learning probability notation and representing probabilities using standard notation like PA for the probability of event A. We have also learned the addition law, and we have understood how to use visualizations of probabilities, including Venn diagrams, tree diagrams, or other visual tools. With this groundwork in place, we are ready to explore conditional probability. This technique is essential for solving problems where we need to determine the likelihood of an event occurring given that another event has already taken place. For example, imagine someone has tested positive for a disease. You know that the test sometimes gives false positives, where a patient tests positive despite not having the disease. Accordingly, you want to know the probability of the person having the disease given that they've tested positive. With conditional probability, we can precisely answer such questions. And as this example highlights, answering these sorts of questions is essential to fields ranging from medicine to law. This sort of conditional probability was particularly important during COVID-19, for instance. Let's dive into this fascinating topic and equip you with the tools you need to tackle even more complex probability problems with confidence. Conditional probability is the measure of the probability of an event occurring, given that another event is already known to have occurred. This concept helps us refine our understanding of the likelihood of events based on additional information. Suppose we have a bag with the numbers 1 to 10 inside. Consider drawing a number from the bag. Given that we drew a prime number, what is the probability the number is also odd? Here, our focus is on refining the sample space to the part that encompasses the event we know has occurred. In this case, drawing a prime number. First, write out the sample space, the complete set of outcomes. For this example, our sample space is the numbers 1 to 10. Next, restrict the sample space based on drawing a prime number. The prime numbers within our sample space are 2, 3, 5, and 7. Thus, our restricted sample space based on drawing a prime is 2, 3, 5, 7. We can then count the outcomes within this new sample space that meet our criteria. Within this restricted sample space, the prime numbers that are also odd are 3, 5, and 7. So, 3 out of the 4 possible outcomes are odd primes. Therefore, the probability of drawing an odd number given that a prime number has been drawn is 3 over 4, or 0.75. We can also interpret this question with a Venn diagram. Let's denote the probability of drawing an odd number as P brackets A. Then let's denote the probability of drawing a prime number as P brackets B. We can then draw a Venn diagram by drawing 2 overlapping circles. The circle on the left represents A, which are the odd numbers. The circle on the right is for B, which is the prime numbers. Place the numbers from 1 to 10 in the relevant part of the Venn diagram as follows. Notice that the numbers which are neither odd nor prime are outside of the 2 circles, but still in the sample space. We want to find the probability that we have drawn an odd number, given that we have drawn a prime number. We can write this as probability of A given B. We start by restricting the sample space to B, since we know that we have drawn a prime number. We can see that there are 4 numbers in B in total, so this is our restricted sample space. Then select the part of the Venn diagram which also satisfies A. We can see that there are 3 numbers in this purple section which satisfy both A and B. Therefore, the probability of A given B is 3/4. From observing this Venn diagram, you can identify the core formula for conditional probability, which is given as shown. This formula says that the conditional probability of A given B is the probability of both happening divided by the probability of B happening. This can be seen as the intersection on the Venn diagram over the sample space of B. We will explore this idea further in the next video. This insight generalizes beyond numbers. Let's consider another familiar visualization tool, a tree diagram. A tree diagram enables us to map out sequences of events and their probabilities. By focusing on the branches that align with our known event, we can restrict our sample space in a similar way as we did with the Venn diagram. Let's revisit the same scenario with a tree diagram. Begin with a root that splits into two branches, prime and not prime. Then split each branch into odd and even. We can then calculate the probability along the branches. Each step narrows down the possibilities, just as we did with the Venn diagram. As we know the number is prime, we can focus on the prime branch, so we consider the numbers 2, 3, 5, and 7. Restricting our search to just this branch, we consider the odd primes. We find that there are 3 numbers which satisfy the conditions of prime and odd. We therefore have 3 odd prime numbers out of the 4 total prime numbers. This confirms that the probability of drawing an odd number given that a prime number is drawn is 3 over 4. By seeing how we restrict our search to specific parts of a diagram, whether that be a Venn or tree diagram, we connect visual representations and the calculation of conditional probabilities. Now let's do some practice problems to solidify your understanding. Imagine we have this Venn diagram showing 2 events, A and B. Event A represents students who play football, and event B represents students who play basketball. The total number of students is 30. 10 students play football, 15 students play basketball, 5 students play both football and basketball, and 10 students play neither sport. We want to find the probability that a student plays basketball given that they play football. This is denoted as the probability of B given A. To find the probability of B given A, we restrict our sample space to only those students who play football. There are 10 students in this restricted sample space since 10 students play football. Out of these 10 students, 5 also play basketball. So the conditional probability is the number of students who play both football and basketball divided by the number of students who play football. This equals 5 out of 10, which can be written as 0.5. Let's consider another example using a tree diagram. Suppose we have a bag with 5 red balls and 3 blue balls. We draw 2 balls one after the other without replacement. We want to find the probability that the second ball is blue, given that the first ball was red. First, let's draw the tree diagram. The first branch splits into drawing a red ball, which has a probability of 5/8, and drawing a blue ball, which has a probability of 3/8. If the first ball is red, the second draw has 4 red balls and 3 blue balls left. So there are 7 balls overall. The probability of drawing a red ball is now 4/7, and the probability of drawing a blue ball now is 3/7. If the first ball is blue, the second draw has 5 red balls and 2 blue balls left. The probability of drawing a red ball is now 5/7, and the probability of drawing a blue ball now is 2/7. We need to find probability that the second ball is blue, given the first ball is red. From the tree diagram, if the first ball is red, the probability of the second ball being blue is 3/7. So this is our answer. These examples demonstrate how to apply the concept of conditional probability by restricting the sample space to a specific part of a diagram. The key is to focus only on the subset of the sample space that meets the given condition and then calculate the probability accordingly. Before we finish our lesson, let's explore the historical background of conditional probability. Did you know that the concept of conditional probability was significantly developed in the 18th century? Thomas Bayes, an English statistician, introduced the foundational ideas, which were published posthumously in 1763. Pierre-Simon Laplace, a French mathematician, later expanded on Bayes' work. In astronomy, Laplace used conditional probability to predict the stability of the solar system and to refine the calculations of planetary orbits. In legal judgments, he applied these principles to assess the likelihood of various scenarios based on available evidence, thereby laying the groundwork for modern forensic science and statistical reasoning in legal contexts. Laplace's contributions helped establish conditional probability as a crucial tool in both theoretical and applied mathematics. In today's lesson, we explored the concept of conditional probability and how it differs from general probability. We learned how to refine our sample space based on known events, using visual tools like Venn diagrams and tree diagrams to aid our understanding. By focusing on a specific part of the sample space, we can accurately calculate the probability of an event occurring given that another event has already happened. We illustrated this with an example of drawing an odd number from a bag, given that a prime number has been drawn. By restricting our sample space to only the prime numbers within the initial set, we determined that the probability of drawing an odd number is 3/4. This process was also demonstrated using a tree diagram, which helped us visualize the sequential narrowing down of possibilities. The key takeaway is that conditional probability allows us to make more precise predictions by considering additional information and restricting our sample space accordingly. This technique is invaluable for solving complex probability problems more effectively.